is going to be a demonstration for project 27. What we did on Tuesday night, we did the calculations. Now I'm going to go through some of the measurements to prove that the calculations that we did are correct, and hopefully demonstrate a little bit more of the theory of Thevenin's equivalent circuit. So project 27, figure 1, had two 10K resistors hooked up in series, and I do have that already hooked up. I also have identified point A and B, which turns out to be our Thevenin output, and I'm going to measure the resistance across the two resistors and prove that they are 10K each, which would come out to be approximately 20K. So I'm going to go through that now. First, I have to make sure I remove the power supply. And there you can see, if I move the wire, I have approximately 20K. Not too bad for what we're doing. So, again, I'm connecting across the two 10K resistors to give me approximately 20K, as needed for the circuit. Now the next part is to hook up a voltage of applied voltage of 20 volts. I already have that adjusted, and I'm going to go to the voltage measurement. I'll put it on the 200 volt scale, and then I'm going to just turn on the power using the voltage measurement across the entire circuit. And I have that adjusted for approximately 20 volts. And I have that adjusted for approximately 20 volts once I hook up the power supply. And there it is, actually 20 right on the nose. Okay. So now, one of the things we had to do was to measure across point A and B. And again, A and B, I'm calling this R1 and this R2. So A and B, output A and B, which is the Thevenin output, I'm going to measure that voltage, and that would be equivalent to my VTH, my Thevenin voltage. So if I just take the black lead of the voltmeter and move it over to the B point, and we look at the voltmeter, you can see we have 10 volts. Okay, and if you remember Ohm's law, if we take a applied voltage and the voltage divides equally among two equal value resistors, so we have 10 volts on one and we should have 10 volts on the other, and I could prove that right now. And there we are. Okay, so now I'll put that back on A and B. And now what we're going to do is determine the RTH. And the RTH, the Thevenin resistance, tells me there's a certain method I have to use, and that is to remove the power supply and then put a jumper where the power supply was. So the power supply was originally connected. I know I already removed, I didn't remove it yet. The power supply is connected from point A over here to the end of the other resistor, R2. So I'm going to turn off the power. And then we're going to remove, I only need to remove one of the leads for the power supply. And then I'm going to put a jumper in there. And that jumper is going to go where the power supply was, which is from the top of R1 to the bottom of R2. And what that does is effectively put R1 and R2 in parallel with each other. So now, if I measure the ohms across point A and B, I should get two 10Ks in parallel, should give me 5K. And that is identified as the RTH. So I'm going to take my meter, go over to the ohm scale, and the meter is now reading approximately 5K, 4.92. And that pretty much proves what we did the other night on the measurement, on the calculations. So that would have been the observation of part 2, voltage A to B, and also part 3, where we identified the RTH. And now we proved it with a measurement. And then we conclude by filling out the Thevenin equivalent circuit, which consists of a VTH power source and an RTH series resistor. And again, the VTH 10 volts, the RTH 5K. Now the next part, part 4, we were supposed to hook up a 10K resistor. Well, just calculated what it would be. And we came out with a calculation of IL of 0.67 milliamps and a VL of 6.7 volts. And step number 5 says to actually do it. So that's what we're going to be doing right now. So we're going to turn off, power's off. I'm going to take a 10K resistor. First I remove that jumper again. Take a 10K resistor, and I'm going to put it in parallel with R1, which is where the identifying A and B is. So I'm going to put it over here, put it over here. So now I have a 10K in parallel with R1, which is point A and B. I still have R2. I'm going to hook up my ground. I didn't change the voltage. So now what I could do, go back to voltage. And I'm going to turn on the power source, power supply, and see what kind of voltage I get. We expected to get 6.7 volts. So let's see what happens. And we got 6.64. Not too bad for what we're doing. Again, there's always a tolerance. Is the resistor exactly 10K? Probably not. Am I putting in exactly 20 volts? I could recheck it, make sure it didn't drift. But we're pretty close to what we should have. So that would be the Thevenin voltage across point A and B. Alright? And now what we're going to try to do, and that would be the observation for step number 5, where it says VL is 6.7. Again, I could measure VA. We can do that right now. And VA should be across the entire circuit just by moving the ground lead over there. And we have pretty close to 20 volts. So that really did not change much. Going back to point B, I now have my 6.65 volts. And the other part of that was to determine the IL, the load current. Now the load current is going to be the current only going through that 10K resistor that I added. So I have to make sure I'm measuring only that point. So what I'm going to do is I'll turn the power off. And I'm going to lift the load resistor lead, because to measure current I have to actually put the current meter in series with the component I want to measure. And I don't care about the voltage right now. I have my, I'm going to use the yellow lead, which is going to go to this point right here. Why am I choosing that point? Because that's where the current, remember the current's going to come from my power supply, come into the R2. At that junction point, some of the current's going to go through R1, some of the current's going to go through RL. I want to see how much current is only going through the RL. So now what I'm going to do is I hook that up to that point where they split. The current comes up to that junction point, and I want to determine how much is branching off into the RL. So I'll take that. The black lead of the ammeter goes to here, which you have a yellow jumper right now. And the red lead, or the positive lead, which I'm using white, is going to go to the RL. And now I should be measuring only the current going through RL. And if I turn this on, we'll see how much current I get. And lo and behold, I have approximately 0.67 milliamps. And we calculated 0.67. So we're very close to what we should have. So that proves that the calculations that we did the other night are correct, because we just proved it through the measurements, and the measurements prove the calculations are correct. Okay, the next step was to take the 10K load resistor out and put in a 4.7K. So we're going to turn the power off. I'm going to remove this. I'm going to get a 4.7K. And I'm going to put that in place of the 10K on point A and B. Now to speed things up a little bit, I'm going to reconnect. I'll remove one lead again of the load so I could measure. I have the ammeter still hooked up, the red lead, the black lead rather. Here's the black lead of the ammeter going into the junction point where the current will come in and split. Some will go through R1, some will go through my new load resistor of 4.7K. So I'll take the red lead. Current's going to go flow up to this point. Now current's going to flow into the meter. I have an open circuit. Current's going to flow into the meter, out of the meter, connecting to my new load resistor, and that should tell me how much current I'm going to draw on that particular point. And because these two are going to be in parallel, the voltage should be the same whether I measure at this point, or across the RL, because they are in parallel. Okay, so I'm going to turn the power on and we're going to see what we get. So, voltage, I now have 4.89 volts, and that voltage is measured across, right now I'm physically connected to R1, but even though I lifted the RL lead, they are in parallel through connection of the ammeter. The ammeter is just measuring the flow of current going through RL. And the theoretical value would have been 4.84 volts. And the current should have been approximately 1 milliamp, 1.03, the theoretical value. And we're pretty much right on target with that, 1.03. See if the lighting helps here. No, that made it worse. Okay. So, as far as measuring the new load current and voltage, it's right on track with what we expected. VL calculated should have been around 4.8. IL calculated should have been around 1.03, and we're pretty much right on target with that. And the conclusion, did the measured and projected values, this is step 7, did the measure and projected values for VO reasonably compare? Yes, they did. Were the calculations made easier by virtue of the Thevenin equivalent circuit? The answer to that should be yes, even though you may feel otherwise. And so that worked out pretty well. All right, step number 9, or actually step number 8. It says connect the circuit as shown in figure 27-2. Now here, we're going to have to add a few more resistors, and 27-2 we're going to end the experiment right here because I don't have enough time to demonstrate that right now.